Okay, let's unpack this. If you just bought a massive 65-inch 4K television for your living room, there's a very good chance the screen on the 5-year-old phone sitting in your pocket right now is actually much sharper.
Yeah, which sounds completely backward, right?
It really does. But welcome to the deep dive. Today, we are pulling from a highly comprehensive set of IT certification training notes from Professor Messer. Specifically, we cover CompTIA, A+ display attributes and types.
Right, and we should clarify, the goal here isn't to prep you for an IT exam.
Exactly. The mission is to decode the marketing jargon you see at Best Buy or online so you can actually understand the absolute magic happening beneath the glass you spend, 8 to 10 hours a day staring at.
It really is a form of everyday magic. I mean, when you look at the sheer variety of display technology in these sources, the reef with constantly engineering incredibly complex physical machines just to trick our own biological eyes. We are trying to see three-dimensional reality on a completely flat surface.
Tricking our eyes. I love that framing. But before we get into the math of why your old phone might look sharper than your shiny new TV, we need to understand how these screens actually generate light and color in the first place.
Right, the absolute basics.
Yeah. So the foundation of almost everything we use today is the LCD or liquid crystal display. When I was going through the source material, I kept trying to visualize the mechanics, and I landed on this analogy. It's essentially like shining a flashlight through a stained glass window.
I like that.
You have a constant white backlight in the rear, and in front of it, you have these microscopic liquid crystals and color filters acting as the stained glass, bending and coloring that white light to create the image.
Well, the stained glass analogy captures the broad strokes, but the actual physical mechanism is even stranger.
Wait, stranger how?
Because liquid crystals are a completely unique state of matter. They flow like a liquid, but their molecules maintain a structured, crystalline order.
Okay.
So in a monitor, you have your backlight shining white light forward. That light hits a vertical polarizing filter, which only lets light waves oscillating in a vertical direction pass through.
Like vertical blinds on a window.
Exactly. Then, the light hits the liquid crystals. When your monitor circuitry applies a tiny electrical voltage to a specific pixel, those crystal molecules physically rotate.
They physically move.
They do. And as they rotate, they twist the light waves 90 degrees so they can slip through a second horizontal polarizing filter on the front.
Oh, wow.
Yeah, and if the computer cuts the voltage, the crystals untwist, the light gets blocked by that second filter, and the pixel goes dark.
Wait, hold on. If the backlight is always on, just shining a flashlight at the back of these filters, how do you ever get a true black? Even if the crystals twist to block the light, some of that beam has to bleed through, right? It seems like you just end up with a milky, dark gray.
You are absolutely right. You do get a dark gray.
So why didn't we just abandon LCDs years ago if they fundamentally struggle to show the color black?
We tolerate the gray blacks because of massive physical and economic trade-offs. I mean, older cathode ray tube monitors, those massive glass boxes we had in the 90s.
Oh, yeah, the heavy ones?
Right, they could produce great contrast, but they weighed 50 pounds and consumed a huge amount of electricity. LCDs require barely any power.
Which is the only reason laptops and smartphones can run all day on a battery.
Precisely. And they are incredibly inexpensive to manufacture at scale. So manufacturers just tweak the stained glass, to use your analogy, developing different types of LCD panels to mitigate the flaws.
Right. And the notes break those down into TN, IPS, and VA panels.
Yeah, so TN stands for twisted pneumatic. It's an older LCD tech, but it survives because those specific liquid crystals can twist and untwist blisteringly fast.
So I imagine gamers love those.
Exactly. Gamers buy TN panels because that physical speed translates to zero visual lag. But the problem is the geometry of the twist. The light shoots out in a very narrow, forward-facing cone.
Oh, meaning if you move your head slightly to the side.
Or look at the screen from an angle, the light physically misses your eye, and the colors look completely washed out.
Which is incredibly annoying if you're trying to show a YouTube video to someone sitting next to you.
Very annoying. So to fix that, engineers developed IPS, or in-plane switching. Instead of twisting outward, the crystal molecules rotate parallel to the glass panel.
Okay, so it spreads the light out more.
Exactly. It scatters the light evenly, providing rich, accurate colors no matter what angle you view the screen from. The trade-off is that IPS panels are generally a bit slower and more expensive to produce.
And then VA is the middle ground, right? Vertical alignment.
Yeah, better colors than TN, better contrast than IPS,
Yeah.
sitting firmly in the middle of the market.
But no matter how you arrange the crystals, you still have that constantly running backlight bleeding through,
You do.
which leads directly to OLED, organic light emitting diodes. This completely ditches the flashlight.
It removes the backlight entirely. In an OLED screen, the pixels themselves are the light source. The organic part refers to carbon-based film sandwiched between two conductors.
Okay.
When you pass an electrical current through these carbon films, the molecules become excited and release photons. I mean, they literally glow.
So if you want to show a pitch black cave in a movie, the screen just cuts the electricity to the pixels in that specific area.
Exactly. They emit zero light, you get infinite, perfect contrast.
And because you don't need a bulky backlight unit sitting behind the screen, OLED panels can be impossibly thin. I mean, it's the reason our modern smartphones are basically just sheets of glass.
Right. But OLEDs are notoriously expensive to manufacture in large sizes, like televisions, which is where the industry engineered a brilliant middle ground. Mini LED.
Which is an LCD, but the backlight gets a massive upgrade.
Yeah, instead of using a few large LED strips to light up the entire back of the panel, a mini LED display uses tens of thousands of microscopic light-emitting diodes.
Okay.
Because the light sources are so small and densely packed, the monitor's processor can dynamically control them in tiny clusters.
Meaning if half the screen is a dark cave and the other half is a bright sun, the monitor can literally turn off the tiny LEDs exclusively behind the cave section.
That is known as local dimming. It allows a vastly cheaper LCD panel to mimic the deep, inky blacks of a premium OLED simply by turning off the flashlight in highly localized zones.
Okay, so we've covered the mechanics of the light, but packing all those tiny lights together brings up a weird mathematical illusion.
Oh, this is the 4K thing.
Yes, which goes back to my point about your phone being sharper than your TV. We've been trained by marketing to see the label 4K and assume it guarantees a perfectly crisp image. But the sources reveal that 4K is not a measure of physical size or clarity.
No, not at all. It is just a raw head count of pixels. A standard 4K display, assuming a 16 by 9 widescreen aspect ratio, contains exactly 3,840 pixels horizontally and 2,160 pixels vertically.
It doesn't matter if that screen is the size of a tablet or a billboard.
Exactly. It has the exact same number of dots.
And this is where the metric of pixel density, measured in pixels per inch, or PPI, becomes the most important number nobody looks at.
Right.
Let's look at a 27-inch 4K desk monitor. The horizontal width of that screen is about 24 inches. If you take those 3,840 pixels and divide them across 24 inches, you get roughly 160 pixels packed into every single inch.
And at 160 PPI,
Yeah.
assuming you are sitting at a normal desk distance, your biological eye cannot distinguish the individual glowing squares.
The pixels are too small.
Right. They are so densely packed, the image looks like continuous, flawless reality.
But then you take that exact same 4K resolution and stretch it across a 65-inch television. That TV is almost 57 inches wide. You divide the same pixel count by 57 inches, and your pixel density plummets to just 67 pixels per inch.
You have taken the same amount of digital paint and stretched it over a massive canvas.
Exactly. The individual pixels are physically larger and further apart.
Which means if you walked up and stood 2 feet away from that 65-inch television, the image would look atrocious. You would see the jagged, stair-step edges of every curve and letter.
But we don't do that.
Right. This forces us to consider viewing context. You don't sit 2 feet away from a 65-inch TV. You sit 10 or 12 feet away on a couch. Distance acts as an equalizer.
Ah, okay.
As you move further back, your eye's ability to resolve fine detail diminishes, and those large, jagged pixels blend back into a smooth image.
So it's all about how close the glass is to your face.
Precisely. And this mathematical relationship between digital pixels and physical space doesn't stop at the glass. The sources emphasize that if you work on a digital image and want to print it, you are translating pixels per inch on the screen to dots per inch, or DPI, on a physical printer.
Because printers use physical dots of ink.
Yes. So if you have a beautiful image on your monitor that is 72 PTI and you try to print it on a high-quality 300 DPI printer without scaling the math properly, the printer is going to stretch and distort the image.
Leaving you with a blurry, pixelated piece of paper. The physical density has to match the digital density.
Exactly.
So we've got millions of pixels packed tightly together to make a sharp image, But rendering all those pixels perfectly creates a massive data traffic jam the second things start moving.
Oh, definitely.
Because a screen isn't a static painting, it is a rapid-fire slideshow, redrawing itself dozens or hundreds of times every second.
Which introduces the concepts of refresh rates, measured in hertz, and media speed, measured in frames per second, or FPS. Hertz is the physical capability of the monitor.
How many times per second the screen can clear its pixels and redraw a new image?
Right. And frames per second is the speed of the actual content being fed into the monitor.
And we use wildly different speeds for different types of media. Like, if you sit in a movie theater, that massive projector is usually running at exactly 24 frames per second.
Giving it that slight, natural motion blur we associate with cinematic storytelling.
Yeah, exactly. Meanwhile, YouTube videos or standard television broadcasts typically run at 30 frames per second.
But if you are watching live sports or playing a fast-paced video game, 30 frames per second is not enough. Professor Messer's notes include a great visual breakdown of this.
All about the gaps between frames.
Yeah, when objects move incredibly fast across a screen at a low frame rate, your eye actually perceives the gaps between the frames. The object doesn't look like it's gliding. It looks like it's teleporting in choppy, isolated jumps.
So high-speed media requires 60 frames per second or higher to maintain the illusion of smooth motion. Which brings up a massive consumer trap. If I am tired of my video games looking choppy, the logical conclusion is to go out, spend $1,000 on a premium 144 hertz gaming monitor, plug it in, and expect flawless motion.
Right.
But I've done that, and the game still stuttered. The monitor didn't fix anything.
The monitor didn't fix anything because you ignored the system bottleneck. A display is only the final output stage. Think of it like attaching a massive fire hose to a tiny garden faucet.
Okay.
Your new monitor is the fire hose. It is entirely capable of spraying 144 frames a second. But your computer's graphics card is the faucet. If your computer only has the processing power to calculate and generate 30 frames a second, your expensive monitor is just sitting there empty, waiting for data that isn't arriving.
And even if you upgrade the computer so the faucet matches the fire hose, you still have to connect them. The sources are incredibly explicit about the cables themselves being a hidden bottleneck.
Oh, this is where people constantly ruin their own expensive setup.
Really? Just with the cable?
Yeah. To push a 4K resolution image at 144 frames per second, your computer is calculating and transmitting well over 1 billion pixels of color data every single second.
That's absurd.
An older, standard HDMI cable you find in a drawer physically lacks the internal bandwidth, the data lanes, to carry that much information. The data literally backs up in the cable, the monitor starves, and the image stutters.
Wow. So what do you need?
You specifically need an HDMI 2.1 cable, which is engineered with higher frequency lanes to carry that massive data load. Or if you are running dual 4K monitors at high speeds, you need the massive bandwidth of a DisplayPort 2.1 connection.
All right. So the motion is smooth, the bandwidth is clear, and the pixels are packed tight. But how close is the color of an explosion on that screen to the actual physical color of an explosion in real life?
Right. Color accuracy.
The sources dive into color gamut, and honestly, the technical specs make human biology sound vastly superior to our best technology.
Our biology is superior. I mean, the human eye can perceive a massive spectrum of color that no consumer screen on Earth is currently capable of reproducing.
Really?
Yeah. To visualize this limitation, scientists back in 1931 actually mapped the entire range of human color vision. It's called the CIE 1931 color space. And on a chart, it looks like a giant, vibrant horseshoe of color.
And when you look at the technical specs for a monitor, they are essentially telling you how much of that horseshoe they can actually light up.
Exactly. The industry standard is sRGB standard, red, green, blue. On that chart, sRGB is just a small triangle sitting inside the massive horseshoe of human vision.
Meaning a monitor can only display the colors that fall inside that small triangle. Everything outside of it is invisible to the hardware.
Which brings us to the marketing numbers. The notes compare two high-end monitors. One claims 100% sRGB coverage, meaning it can perfectly display every single color inside that triangle. The other monitor claims 95% sRGB coverage.
See, 5% sounds like a rounding error. It feels like something a normal person would never even notice.
Well, a normal person wouldn't notice. If your daily workflow is reading spreadsheets, sending emails, and watching streaming video, a 95% sRGB screen is perfectly adequate. You save money, and you lose nothing of value.
Right.
But if you were a professional photographer, a graphic designer, or a video editor, That missing 5% is catastrophic.
Because you literally cannot trust your own eyes.
Exactly. If the monitor cannot physically display a specific shade of cyan, it will substitute the closest color it has. The editor, looking at an inaccurate image, will push the color sliders too far to compensate.
And then when they export that video and the rest of us watch it on our phones or TVs, the colors will look wildly oversaturated and unnatural.
Precisely. Professionals have to pay the premium for 100% sRGB or even wider standards like Adobe RGB, which usually requires highly calibrated IPS panels or OLEDs.
You know, we have spent all this time talking about looking at the glass, but the way we interact with these devices has completely shifted. We touch the glass now. We ditched the physical keyboard on mobile devices entirely, and that relies on an invisible layer sitting directly on top of the liquid crystals called a digitizer.
Yeah, the digitizer is essentially a microscopic grid of transparent wires. When you tap your finger on the glass of your phone, you are actually disrupting the electrical capacitance of that specific area of the grid.
Like breaking a beam of light.
Sort of, yeah. The digitizer instantly calculates the exact X and Y coordinates of your finger and sends that location to the processor to execute a command.
And high-end digitizers don't just sense broad finger taps. They track a stylus with surgical precision, measuring the pressure and the angle of the pen.
Which is incredible engineering.
It is, but I find it deeply ironic. We have spent billions of dollars researching organic light-emitting compounds, engineering microscopic capacitance grids, perfectly calibrating color spaces, all just to perfectly mimic the feeling of dragging a 50-cent ballpoint pen across a piece of dead wood.
It is funny when you put it like that. The ultimate goal of our most advanced digital technology is often to recreate the analog world we evolved in.
Definitely. Okay, let's pivot to something incredibly practical before we wrap up. We have explored all this cutting-edge engineering. What happens when all these microscopic grids, liquid crystals, and backlights just go completely dark?
The dreaded black screen.
Right. You open your laptop one day, hit the power button, and the screen is black. The sources offer a hardware diagnostic trick that completely shifts how we should handle broken tech.
This is a vital troubleshooting step, particularly if you're dealing with a laptop that is a few years old. We talked earlier about the backlight, the flashlight, and the LCD sandwich.
Right.
Well, many older laptops don't use LEDs for their backlight. They use CCFLs, which are basically tiny, thin fluorescent lamps.
And the technical catch here is power delivery. Those fluorescent lamps require alternating current, or AC power, to ignite. But your laptop battery is essentially a giant block of direct current, or DC power.
So to bridge that electrical gap, the laptop relies on a small circuit board called an inverter. It takes the low-voltage DC power from the laptop and aggressively steps it up, inverting it into the high-voltage AC power required by the fluorescent tube.
That sounds like a heavy workload.
It is. These inverters run hot, they handle high voltage, and they frequently burn out. They're usually hidden right inside the plastic bezel surrounding your screen.
So if the inverter burns out, the liquid crystals might still be twisting and doing their job, but the fluorescent flashlight behind them is dead.
Right, so the screen looks completely black to the naked eye. Which brings us to the flashlight trick.
Yeah, explain this, because I love this.
If you turn on a laptop, here the fans spin up, but the screen is dead. Take a physical flashlight, or the light on your phone, and shine it directly into the dark screen at a sharp angle.
Because you are manually providing the backlight.
Exactly. The external light from your phone reflects off the back of the display assembly and pushes back through the twisting liquid crystals.
So if you shine the light and you can suddenly see the faint outlines of your desktop icons, your mouse cursor, or your wallpaper.
It is a revelation.
Yeah.
It means your motherboard is perfectly fine, your graphics card is generating the image, and the liquid crystals are successfully manipulating the light. The only thing broken is the illumination.
This detail transforms you from a panicked consumer into an active troubleshooter. Instead of assuming the $1,000 laptop is completely dead and throwing it in the recycling bin, you can look up the manual for your specific model and realize you might just need to carefully replace a $15 inverter board in the plastic bezel.
It totally demystifies the hardware. You stop seeing it as a black box of magic and start seeing it as a collection of replaceable components.
Yeah.
Though I will add, if you are opening a laptop bezel to replace an inverter, ensure the device is completely powered down and the battery is removed, as those components do handle stepped-up voltage.
Always respect the electricity. That is exactly why we dive into these sources, to strip away the mystery. So the next time you sit down at your desk or pull your phone out of your pocket, Take a second to look at the glass. You now know it is a dense, microscopic sandwich of twisting crystals and polarizing filters.
Right.
You know that a 4K label is just a raw math equation stretched across physical space. You know that dropping $1,000 on a 144 hertz monitor is useless if you are strangling the data with an old HDMI cable. You can see right past the marketing jargon to the actual physics of the machine.
It really changes your relationship with the objects you use every day. And I want to leave you with a final thought to ponder, something that builds on this entire discussion of how we measure visual clarity.
Okay, what is it?
Right now, our entire paradigm is based on physical boundaries. We measure pixels packed into a 27-inch piece of plastic on your desk. But the tech industry is rapidly moving toward augmented reality and virtual reality.
Where the physical boundaries of a monitor are completely removed.
Precisely. When the glasses you wear project the image directly into the retina of your eye, or seamlessly overlay it onto the physical room around you, we won't be measuring pixels per inch anymore.
Because there are no inches.
There's no flat glass.
Yeah.
Instead, the engineering shifts to measuring pixels per degree of your actual human vision.
Oh, wow.
Yeah. As we abandon the physical screen entirely, and the digital light blends perfectly with the real world, how will our definitions of resolution, clarity, and reality itself change?
Now that is something to think about the next time you turn on a screen.